let's go over this. 12.3, the regression equation. I will say right up front, a lot of the notation in this section for our linear regression equation is going to be kind of clunky, but keep in mind, a lot of this we're going to figure out using technology. So although we have these equations we can use on paper, we're going to be using we're going to use technology to find our linear regression line, our line of best fit, our least squares line, depending on how we want to name it. So let's talk about some data here. We have a random sample of 11 statistics students who produce the following data, where X is their third exam score out of 80 points possible, and Y is their final exam score out of 200 points possible. Can we predict their final exam score for a random student if we know their third exam score? First of all, to be able to predict an outcome, there has to be a relationship between the two variables. And if there is a relationship, then we can do our best to predict, have a prediction given some information. So here's our list of 11 statistics students, their third exam score. Here are their Y exam scores. And if we plot them, it looks like this. Now thinking back at scatter plots, is there a relationship that exists here? All right, I've thrown this into Word just to kind of play around with it to see, can I make a line such that at least a lot of the points are very close to this line? And it looks like I can. They're scattered pretty much close to this line. Now there's a little bit of one that's deviated from it, but I can get a line that's pretty close to this. If I find that line, that is going to be my prediction line. It's just a prediction. What that means is if I say, oh, I scored 78 on my third exam, that would predict you would get, such and such a score on your final exam. It's just a prediction. Because of past experience, we can make a prediction. So it does look like there's some relationship between their third exam score and their final exam score. All right. Our third exam score is the independent variable. Our final exam score is the dependent variable, at least in this scenario. We want to plot a regression line that best fits the data. Keep in mind, it is not going to fit perfectly. It's not going to go through every single point. If it's a line, it just can't do that. It's going to be, if we did try and connect them with all the lines, it's not going to be a straight line. So if we were just to try a line by eye, like I did, how would we draw that line? And you might not draw it the same way as I draw it. The goal is that we have a method of drawing the same line. We want every distance, at least the vertical distance from our line that we draw, to be minimized. The smallest possible distance that we can have from this line for every single point at the same time. Some distances are going to be larger than others. Some are going to be right on the line, but we're trying to minimize those distances. So our point y value minus the line's y value is going to be this error, and it's called epsilon naught. It's an error. Epsilon is a Greek letter. We're going to try and minimize these. We're always going to use the absolute value of our epsilon, and to do that we can either take the absolute value of it or we can just square it. Squaring negative times negative is a positive, positive times positive is a positive. So if we always want our error to be positive, we're either going to square it or we're going to take the absolute value of it. Now, of course, if we're looking at the individual errors, if the point is above the line, then the residual is going to be positive. Our point y value minus our line y value would be positive. And if the point is below the line, then your residual or your error is going to be negative. Again, we're going to ultimately force these to be positive by taking the absolute value of it. Now let's assume these distances have been minimized. We have made the line in such a way that it's the closest to every point possible, and the residuals, these errors, have been minimized. What we're going to do is force them to be positive by squaring each one of them and add them up. That is what's called the sum of squared errors, SSE. Now, if we're using higher math, and we're not, we can make sure that SSE is minimized, but there's a way of doing it using the calculator. So I'm going to skip over that part just for a second and talk about our line is called y hat. Y hat equals a plus bx. X is our value that is our dependent variable, right? A is actually the average of our y's minus b times our average of our x's. And our b value is the sum of x minus x bar, in other words our average, times y minus y bar, all over the sum of x minus x bar squared. That is our b value. B can also be written in this form. R times the standard deviation of y divided by the standard deviation of x. Now remember, our x's and y's are values given. Those are points. Those are data points. So we can find the standard deviation of the y. We can find the standard deviation of x. We can also calculate our b value. Doing all of this, we can solve for this r, which is our correlation coefficient. That tells us how strong the relationship is. And we're going to be using that r value a lot in the future. Now the least squares criteria for the best fit is minimizing this squared errors. That is our least squares line, regression line. There are tons of things out there on the web that will do this for us. Hand calculations, it's totally possible. I'm not going to rely on that. I'm going to rely on technology. Okay, when we have our technology out there, and I'm going to show you one. Here's our good old social science statistics website, and they have a linear regression calculator. So how we're going to work this is we're going to put in our x values. We're going to put in our y values. So here are our x values, 50. Let me go back to our exam scores. Here we go, 65, 67, now that we have our data, and we're going to calculate the regression equation. Okay, now keep in mind, this puts it in the y equals mx plus b. So it's saying our b value for our terms is 4.82739x minus 173.51336. Let me show you what the book has. Negative 173.51 plus 4.83x. Okay, so here we go. All I did was put in my values, and it will calculate it for us. And in fact, the cool part about this is it does give us some summary here. Our sum of our x's is 761. Our sum of our y's is 1765. The mean is given for our x. Mean is given for the y's. Our sum of our squares and a sum of the products. Our regression equation is in this format where y hat equals bx plus a. Our b is given with our SP, our sum of the products, divided by the sum of the squares. Our A is given by the mean of our y's minus b times the mean of our x's. Those are the same equations that are in our book, and that's how they get their equation for our y hat equation, our regression line. Normally I would encourage you, get your hands wet, try this out. But you've already done all of these calculations. You've already figured out sums of values. You've already figured out averages of values. You've already even figured out the sum of squares. So what I would suggest is focus on learning what it means to be a linear, a regression equation versus the ins and outs of how to calculate it, if that makes sense. Okay. Now again, most of these values are, or most of these calculations are going to be done using technology. So let's talk about our slope. Our slope really tells us how the dependent variable changes by our independent variable. That's our slope. It's either a negative slope, a positive slope, or no slope whatsoever. Since our slope is 4.83, for every 1 point increase on the score of our third exam, the final exam score increases by 4.83 points on average. There is a relationship between those two things. Okay, so I am going to go ahead and show you how to do this on the TI-84 calculator. If you're using the web, I highly recommend going ahead and using the social science statistics calculator for linear regression. I will put this up there in our Canvas area so you don't have to go searching for it all over the place. But let's try it with our TI-84. Here's the example we're going to do using the TI-84 Plus. Scuba divers have a maximum dive times cannot exceed when going to different depths. This data table shows the different depths with the maximum dive times in minutes. Use your calculator to find the least squares regression line and predict the maximum dive for a time of 110 feet. Now I am going to go ahead and put my X values in L1, my Y values in L2. Okay, I've entered my data into my lists. I want to go to Stats and Tests. And I do want to find the linear regression t-test. Okay. So linear regression t-test, not the linear regression t-int test. My X values are in L1 by default. My Y list is in L2. My frequency is a 1. I'm going to keep that. And then I'm either going to use a beta or a rho. That's a fancy Greek letter, and beta is a Greek letter as well. And this time I am going to go ahead and keep it on does not equal 0. And I'm going to calculate. That's quick and easy, right? Calculate. Okay. This is all my information that I'm given here for my t-test. And there's a whole bunch of information that I can use. My degree of freedom is 4. My A value is 127.2381. My B value is a negative 1.1143. And let's go down and see what else we're given. Aha! We are given our R value, which is going to be ultra important when it comes to doing some testing in regards to is there a correlation or not, is this R value. Now depending on what your R value is really going to determine if you can say the two things are related or not, meaning that they have a relationship between them. So again, all I did was put in my data in list 1 and list 2, and I selected the appropriate test. So let's now see this graph with our scatter plot. Let's plot our scatter first. So I'm going to go ahead and say second stat plot, and I'm just going to go put it in plot 1. And so I want to make sure that my plot is on, and I'm going to do a scatter plot. My list is L1 for my X values, my Y1 or my L2 for my Y values, and I don't care what mark it is really. I guess I'll just do a dot, and blue is fine. Then I'm going to go ahead, and it honestly doesn't matter that I hit my values, I'm going to go ahead and click on number 9 for zoom stat, and here is our plot. Now hitting that said fix my window to whatever you need it to. Now I want to graph the best fit line. Go ahead and go line, and my values are 127. It won't put it in there for you. You have to kind of mark it down on the side. And I wrote it down on a piece of paper so I could see what it is. Minus 1.1143 x value. X value is right. And then I'm going to go ahead and say zoom and number 9 to graph it that as well. Okay. So we can see our scatter, we can see our best line of fit. And you can see there are no dots that are actually on the line. Probably should have graphed those in green maybe. But you can see that they're close. They minimize the distance between every single point, y value, and the line itself. Now I'm going to go back to that test that we just did. And it was F. I'm not going to change anything. I just want it to recalculate it. And I want to talk about this R value. This R value is what's called the correlation coefficient. This tells us a measure of strength in the direction of the linear associated with it. So if it's negative, that means there's a negative relationship. If it is positive, there is a positive relationship. This R value is always in between -1 and +1. The closer it is to 0, this value, it means that there's really no correlation. If it is close to -1, it means that it is a very strong negative correlation. If it is closer to 1, it is a very strong positive correlation. Now, with that said, if it is a -1, that means it is a perfect negative correlation. And if it is a +1, it is a perfect positive correlation. Now, I've talked about correlation, and I haven't really said what it means. A correlation, if it is a positive correlation, it means as x increases, y tends to also increase. And if it is a negative correlation, that means as x increases, y tends to decrease. They do the opposite effect. So when x decreases, y tends to increase. As x increases, y tends to decrease. And also with a positive relationship, even though when x increases, y increases, well, when x decreases, y decreases as well. They do the same thing in a positive correlation. When it is a negative correlation, they do the opposite of one another. It does not mean that one causes the other thing. It doesn't mean that x causes y or y causes x to happen. It just means that there's a relationship between them. Now, I also want you to take a look at this R squared value. This R squared value is called the coefficient of determination. When this R squared value is expressed as a percent, it represents the percent of variation in the predicted variable. It explains the variation in the independent variable. 1 minus R squared, when expressed as a percentage represents the percent of variation in y that is not explained. So you can see with r's, R squared is 0.9273. That is so close to 1. It represents the percent, so that would be 92.73% of the variation can be explained by the variation of the independent variable. It's explained by our x's. This large value, this 92%, is explained by our x value. Now, 92.73, so let's say, we'll just call that 93. So 7% is not explained by our linear regression, only 7%. Let's consider our final exam example, and I'm going to plug that into this calculator really quickly. All right, I've keyed in my data. I'm going to go back to stats, run our test, and go to our test for F. List 1 does have my X value, list 2 does have my Y values, frequency is 1. I'm going to keep everything else the same. All right, so our best fit line would be, in terms of our book, would be a negative 173.5134 plus 4.827 for X. Our R value is 0.6631, meaning it has a positive relationship. Our coefficient of determination is 0.4397, meaning 43% of the variation in the final exam grades can be explained in the variation of the third exam grades. Now, 1 minus this 43.57, let's say that's 44%. About 56% of the variation is not explained by the third exam scores. So this variation in the final exam grades cannot be explained by the grades on the third exam using this best fit regression line. So it's a little bit more scattered than we would want it to be. All right, so that is it for this lesson. Until next time, be seeing you.